Hey, Saul.
Hey,
How's it going?
good, I guess.
Good. Today, all you have is your summative on.
Somebody, right?
Yep.
Dang. It's cause like I need help with like stuff, cause like I don't really understand anything.
Okay, so let's go through stuff. What do you want to work on?
You told me we're supposed to do the. Wait, let me check my notes. The parts of the atom day one and stuff.
Okay, so that stuff is not going to be on the summative for today. The
Oh
only,
yeah, but I was just saying like I don't know
okay,
like what to start like to do
for the summative today,
or just any somebody overall.
just any summative. So I would recommend that you're working on the stuff for this unit because if you do the stuff for this unit, then and you do the summative by Sunday, then you don't have to retake. Uh, then you wouldn't have to retake the test if you do well on this stuff, which means that it would just be one less thing you have to worry about later on. So if
Mhm.
you look at the stuff for this unit, we have ionic and covalent bonds, drawing, naming them, and writing the formulas for them. So have you been going through any of this unit stuff?
No, to be honest.
Okay. So we started this unit on week 12. So if you go to Canvas and you go to week 12, November 2nd through the 6th is going to be the stuff that we've done for this unit.
On modules or like
If you go to pages or modules, either
oh
way, you
yeah.
find the weekly agenda. If you go to week 6 or 12, I'm sorry, you go to week 12, that's where all the stuff we've been working on for this unit is going to start.
Oh yeah, week
And
12.
so anything that is got a live Zoom meeting, pretty much, most of those are going to have videos that go along with them that go through at least the introduction stuff. But what we could do today is because you're here, we could go through some of that stuff together now. That way you can ask questions and you're not just like watching a video. Would you like to do that or do you just want to watch the videos?
I like to do what you said.
All right, so let's go through it. Do you want to start on the intro to ionic bonds? Do we want to start there?
Sure.
Yeah, we okay with that?
Yeah, yeah.
Perfect. So let's open that up. Oh, I was working on it earlier. Let me clear this. Let me erase everything. Actually, let's just. All right.
Yeah, all this stuff seems confusing to be honest.
All right, we'll go through it all. Ah. I'm glad you're here and you're coming in to work on this stuff. It's great to see. All
I
right.
know I've done it earlier, but
I
I don't
wish,
know.
but I mean, it's all right. As long as we're getting to it at some point, it's better than never, right?
Yeah.
So the biggest thing for ionic bonds and covalent bonds when we're identifying the type of elements we have. So we have to follow this guideline of ionic bonds are going to be a metal and a non-metal. Covalent bonds are going to be two non-metals. So let's just write that down up here. Covalent equals two non-metals. Ionic is going to be a metal. Oh, can't spell. Plus a non-metal. All right. So we need to be able to identify where our metals are and where our non-metals are. If we're looking at the periodic table, the best way in order to do that is going to be to follow this metalloid line that exists. It's like an imaginary staircase between elements separating our metals from our non-metals. So if we're looking at this wonderful staircase, we are going to draw a line right between boron and aluminum, and then we're going to create this staircase right here. And so if we're following this staircase, anything on this side, the left side of the staircase, is going to be a metal. And anything on the right side of this staircase is a non-metal. So they're going
What is
to
what does it mean with like non-metal?
so some of them are metals, like the normal ones that you can think of are like aluminum and lead and stuff like that.
Oh,
So
yeah.
those are metals because of how they interact with things. So metals and non-metals interact differently. Metals are very malleable, so like bendable, and we can like use them to do things, and they conduct electricity and heat. So they're the reason that things are like electricity runs through wires, because the wires are made of copper. That's they conduct that electricity. Non-metals are very ductile and they're very fragile. So they like break apart pretty easily. They don't like to conduct electricity or heat. But those non-metals, a lot of them are gases, and a lot of them make up like our body is made up of mostly non-metals because it's made up of water and then a lot to do with carbon. So our body has a lot of non-metals inside it, which is why they do different things, because they interact with the rest of the world in different ways. That's why we consider the metals on that left side and the non-metals on that right side.
All right.
The one exception to this metal non-metal line is going to be our wonderful hydrogen is a non-metal.
Oh.
So hydrogen is going to be our only exception to this rule. Hydrogen is a non-metal, even though it's on the left side.
Mm-hmm.
Okay.
So that's the only one on the left side that's non-metal.
Only one on the left side that's a non-metal. Everything else from here, all this stuff in here,
Yeah,
all
yeah.
these ones down there, those are all metals.
Wait, so what about the stuff on the right that's like highlighted, like 7, 8, 9, 17, 35, 53?
Okay, so those ones are special non-metals. So anything highlighted is called a diatomic. And what that really means is that if we find them in nature and we're looking for just oxygen, we'll never find oxygen by itself. We'll never find hydrogen by itself. We'll never find nitrogen by itself. It always wants to be attached with something else. So if it doesn't have anything else to attach to, they're going to attach to themselves. They're going to bond with themselves. So if I write the name oxygen, the thing that we breathe in, the thing that keeps us alive, is not just O, but it's actually O2, because it never wants to be alone. It doesn't like being alone, so it always has to pair up with something. So if oxygen's bonding with sodium, it's happy. If it's bonding with strontium, it's happy. If it's bonding with another non-metal, it's happy. If it's alone, it always has to be a pair.
Mm-hmm.
That's why those are highlighted. So when we're doing ionic bonds, we have to worry about ions. So ions are elements that have gained or lost valence electrons.
What does that mean, valence electrons?
All right, so valence electrons, let me write that way up here. Valence electrons are the electrons in the outermost row or outermost orbital. So when we look at our orbitals, we are talking about the rows. So when we count our orbitals, this is the first orbital going across. These two are in the first orbital. Then the second orbital is these 8. Then the third orbital. And we keep going all the way. There are 7 orbitals that we can. Now, there are some special ones that don't follow our lovely patterns. So we have to worry about those a little differently. The special, what were you saying?
No, no, nothing.
No, you were about to say something. What was it? Because I think you knew it.
I just said, I didn't really say
Oh,
anything.
okay. I thought you were saying a word, which was the transition metals. So these metals right in here, this section, these are a specific type of metal called transition metals. And they do not act like the rest of our elements because our valence electrons don't follow a pattern in here.
All right.
So let's label those transition metals. Valence electrons don't follow a pattern. So, oh. Right. The rest of our elements, it's going to be pretty easy to figure out the number of valence electrons for pretty much every other element. If we're going through our elements and we're trying to find the pattern, we just follow the columns. So this first column is the start of our new orbital. If we were drawing those Bohr models, we would have a new orbital starting with a new valence electron every time we get in this first column. So if we're numbering our valence electrons, this first column has one valence electron. I'm going to write VE for valence electron. So this first column, all of them have one valence electron or one electron in their outermost orbital. The second column, how many do you think they're going to have?
I don't even know.
Take a guess. Doesn't have to be right.
But like I don't even know like what to say. Like
Give me a number. If the first column has one, how many would the second column have?
just two. I mean
Two.
two.
Two valence electrons. All of those elements have two valence electrons.
All right.
Okay. After that, we're skipping everything from 3 to 12. So everything in columns 3 through 12, we are ignoring when we count our valence electrons. So then we start with column 13. Do you have a guess as to how many valence electrons are going to be in column 13?
Would it be 13 or?
It's not going to be 13 because if we count, we're just going to count across that second row. So look at the second row or the second period right here. If we're counting from lithium, beryllium, boron is the next one. So how many valence electrons is that going to be? Or how many spots have you gone through?
Like, what do you mean for two? Like
for row 2. So we have one valence electron in lithium. Then beryllium has two valence electrons. So the next element in that row is boron. How many valence electrons would it have?
Would be the number on top of that 13? Or?
It's not going to be 13. So let's just count. How many have we circled so far in that row?
Only three.
So it's going to have just 3 valence electrons because we skipped this entire section. Since we skipped the transition metals, we don't have to worry about them. So the next row is going to have 3 valence electrons. What about the column 14? What do we think about column 14?
What do you mean by that? Like
how many valence electrons would it have?
Column 14.
Right here.
Whoa. Just 4?
4, perfect. What about the next column?
Then like just 4, 5, 6, 7, or
yeah. And then the last column, column 18.
8.
How many? You said
8, right?
Yep. 8 valence electrons. All right. So 2 more things I want to talk about with valence electrons. This one right here, helium, is also special. So hydrogen and helium do not follow our lovely patterns of everything else. Helium only has 2 valence electrons. Okay. Helium only gets 2 and then it's done. And then the second thing is that all elements want a full valence shell, or 8 valence electrons. So all of our elements want a full valence shell, or they all want to reach this column 18. They all want to have the same number of electrons as that column.
Mm-hmm.
So the exception again is going to be that first column, that first row only has 2. So that means hydrogen only wants 2 valence electrons to be happy or to be stable. This makes them stable.
So if they have less than 8, like, what do you mean by that? It makes them stable?
So if they have 8 valence electrons, they're stable, they're happy. If they don't, they're not stable. So every element that's not in column 18 is not stable yet. They want to be stable.
Like the first one is not stable then.
Correct. That first column is not stable. So in order to become stable, that's why we create these bonds so that they can become stable. We're trying to get them to that valence shell or to have 8 valence electrons so they're all stable. So that's this question right here, actually. So
we need both.
Make all elements.
Wait, what is this that we're working on? Like, what's the name of it?
Oh, this is our Intro to Ionic Bonds, that November 2nd.
All right. Should I, like, I don't even know. Hold on.
So you can work on it on that paper. I can send you the video once we're done. I can make the video and like put it on YouTube and then share it with you. That way you have it so you can go back to it again and you can reference it when you're going through it. Either way is fine with me.
All right.
Okay. So if we go back to that worksheet, so all elements want to make all elements stable by having 8 electrons or 8 valence electrons. This is known as our octet rule. So it's known as the octet rule, or that they all want 8 valence electrons to be stable or to be happy.
Wait, what does the question mean though? But like saying, why do we need both?
So
like
that's based off of those first 2 parts, which I haven't actually gone over yet. But the first 2 parts that we're going to go over in a second, and it's asking why we need a cation and an anion, or a metal and a non-metal and ionic bonds.
Mm-hmm.
So a cation is going to be a positive ion.
And the other one negative or something?
Yeah, the other one is negative. Perfect. And it's a positive ion because it lost valence electrons. And so how would you make a negative ion?
Like it didn't lose valence electrons?
So if it didn't lose, what's the opposite of losing?
Make like, what do you...
So if you didn't lose it, instead of losing it, what could happen with those?
You found it.
You found it, or you gained it. So gained valence.
I was trying to like say a different word than found, but I just couldn't remember.
You're good. Found is a great word for it. You can use found. It's the exact same thing. So you need both of them, because what happens is if one is losing it and the other one's gaining it, they're really transferring that electron from one atom to another, because electrons don't just magically appear and disappear. They just can't do that. They have to come from somewhere or go somewhere. So in our ionic compounds, we are going to be gaining and losing electrons between our metals and our nonmetals. So before we continue on to the next page, I do want to talk real quick about, let's just pick an element. Let's go with potassium right here, number 19. So if you remember from beginning of the semester, this 19 tells us the number of protons and the number of total electrons. That's the exact same number. So potassium has 19 protons and 19 electrons. Potassium has 19, but in the most stable it could be would be that it would have 8 valence electrons in its outer shell. How many does it have right now? How many valence electrons
Wait, which one?
for potassium? Okay.
Oh, that I'll say just one or.
It has one, right? Because it has one valence electron because it's the first one in that column. So my question to you is if it wants, so it wants to gain or lose electrons. Do you think it wants to gain electrons or it wants to lose valence electrons?
If
Because it wants to have 8.
it
So
wants to have 8,
it,
so it will like to like, but like doesn't it have more than 8?
it has 1, right? So in its outermost orbital, it has 1 valence electron. Does it want to
Mm-hmm.
gain more valence electrons or does it want to
Yeah,
lose that one?
it wants to gain.
Okay, so it can go either way. So we have to determine which way it's going because remember, we could have positive ions where it lost electrons or negative ions where it gains electrons. So if it gains
Oh.
electrons, it's going to go from 1, 2, 3, 4, 5, 6, 7 to get to this spot to gain that many electrons. So it would have to
Mm-hmm.
gain 7 valence electrons in order to be stable to have that 8 valence electrons.
Wait, but why do you skip through the part you highlighted?
Because remember, no pattern, we skip over those. If you go back to the trends unit, this is actually, these electrons don't go in the same spot. So they don't
Oh,
go in that outermost orbital.
yeah,
And
all
that's why
right.
we skip over them.
Mm-hmm.
So then if we wanted to gain, we'd have to gain 7. If we lose 1, because if we gain, we'd be at 30, we'd be over here. But if we lost 1, how many electrons would we have then?
7.
If we lost 1 from this 19.
Oh, then nothing. Then I don't know.
If we lost 1 electron, how many electrons will we have? If we
Out of like all the 7 that you counted,
nope, just from
or just
19,
that one.
just from 19. If I lost 1, where would I be? What number?
I don't think it will be 18, would it?
It would be 18. You're right.
Oh, all right.
So then if we find 18 on the periodic table, where is that?
Over here, like all the way by the other right.
Yep,
Yeah.
right there. So it can gain 7, and then it would be in that last column if it gains 7 valence electrons. Or it can lose 1 valence electron, and it would still be in that last column. Which one was easier for us to do? Gaining 7 or losing 1?
Losing 1.
Losing 1 is always going to be easier than trying to gain 7 more. So what's going to happen is, in general, so this is the rule for all of our elements, metals are always going to lose electrons.
Oh.
Metals are always our positive ions. They're always the ones that are going to lose those electrons because it's going to be 4 or less. So it's easier to lose those 3, 2, and 1 electron than it is to gain 7, 5, or 6 electrons. But our non-metals are over here, right? Our non-metals are this section over here. So they're super close to 8. So if I am at like fluorine, it has 7 valence electrons. The easy.
Wait, what about 117 and 118?
117 and 118.
In the bottom right, what does those count as? Metals or non-metals?
Those are. I'm actually not positive about 117 because those ones were discovered in the last like 4 years. I will never give you those. Never ask you to worry about those. These ones on when I was learning chemistry and like in college and high school, those ones didn't have names. Those ones were discovered in 2017. I believe they were given names. So we don't have to worry about those. I will never ask you about those ones.
Oh, right.
So if I'm looking at fluorine now, right over here, it has 7 valence electrons and it wants 8. Is it going to want to try and lose 7 and to go all the way back to get to here? Or is it going to want to gain 1?
Again, once as you said,
Gain 1.
metals always lose.
Exactly. So our non-metals are always going to gain electrons in ionic compounds. So these are always our non-metals. Right here. Are there any questions on that so far? I know I threw a lot at you so far. So I just want to check to see how we're doing.
I think I'm all right for now.
Okay, perfect. So now when it comes to drawing these, so we have to be able to draw these compounds. We have to know how to draw these Lewis dot structures. Do you remember how to do that?
No, I do not.
Okay, so let's go through that just in general first. So Lewis dot structures. If you're talking about those, we have to include 2 things. One is the element symbol. So that's the 1 or 2 letters that represent that element. So if we're looking up here, all of these are represented by their element symbol right now.
Mr. Z, my iPad froze and I couldn't hear.
Oh, I'm sorry.
My iPad froze and I couldn't hear anything.
So the 2 things we want to include, the first thing is our element symbol, which is just those 1 or 2 letters that represent our element. So all of those right up here, these are in our element symbols already. Like potassium's letter is K, sodium is Na, barium is Ba, radon is Rn, argon is Ar. All those are already an element symbol. The second thing we need to include are our valence electrons. So that's that number 1 through 7 around our periodic table. And we kind of do them in a special way when we mark these valence electrons. They're represented by dots. So if I have element X, that's not a real element, but if I am going to label my valence electrons, I start at my top, I go 1. That's 1 valence electron. Then 2 goes here. We go clockwise around our elements. So then 3 would go down here. Then 4 right here. And then we're going to pair them up. So then we go 5 right here, 6, 7, and 8. Because remember, we can only have up to 8 valence electrons. So it goes 1, 2, 3, 4, 5, 6, 7, and 8 for any element. So now, if we're trying to draw the Lewis dot structures for sodium and for chlorine, let's go back up here. Do you remember which element sodium is?
Wait, where is it at?
Sodium is going to be this one, number 11. So our element symbol is Na. And how many valence electrons do we have?
Just 1.
Just 1. Perfect. So we're going to write Na. And we're going to put 1 valence electron on it.
Well, what does Na stand for?
Na stands, that's
what does it
mean? Symbol for sodium.
Yeah, I remember.
So that one is sodium right there. And then we need to find chlorine. Chlorine is up here. That's going to be element number 17, or Cl. So how many valence electrons does chlorine have?
7.
7. Perfect. You're crushing it. Cl. So we're going to go 1, 2, 3, 4, 5, 6, 7. All right. Now, sodium, does it want to gain more electrons or does it want to lose electrons?
It want to gain.
So right? Sodium wants to gain electrons?
Oh, sodium? No, it wants to lose.
It wants to lose its electrons, right? And what about chlorine over here?
It wants to gain.
It wants to gain
electrons. Since it's non-metal.
Because it's a non-metal. Awesome. So In order for both of them to be happy, sodium wants to lose all those dots, and chlorine wants to have 8 dots around its atom. So what we could do is show that sodium is going to give its electron to chlorine. So we're going to draw a circle around that dot, and then we're going to draw an arrow showing that sodium is giving its electron to chlorine.
Mm-hmm.
So now we've created ions. So sodium has lost 1 electron. So we're going to put a 1 up here. And is that 1 going to be a positive 1 or a negative 1? Do you remember?
-1 since it's losing, right?
All right, so that's the trickiest part. When we lose electrons, electrons have a negative charge, which means we're
Yeah, you
losing
put
a
the
negative
positive.
charge. So we got to put a positive in front of our 1.
All right, so since Na is sodium is a non-metal, right?
Sodium is a metal.
Oh yeah, the ones on the left are metal. So since it's metal, it's gonna gain. If it loses, you're gonna like put a plus, and then what it loses.
Yeah.
All right.
All right, so chlorine, is that going to have a positive or negative charge?
A negative.
A negative charge. So a negative 1. But for chlorine, what we do have to include is all 8 valence electrons. We need to show that it gained electrons by putting
You put the 8 of them.
all 8, that it gained that 1 electron. And just so we can keep those valence electrons only on chlorine, we do need to include brackets between our chlorine and our sodium, so we can show that the chlorine is the only thing with those valence electrons.
All right.
Okay.
Wait, so what if, like, for example, like if sodium had like 2 electrons or whatever, like 2 dots, and chlorine only has 7, and you're trying to get 8, what do you do with the other one that sodium has?
What do you think would happen? Let me ask that.
I don't know. I feel like sodium would give the other one to like give 1 electron, right? That's what it's called.
Yep.
And sodium would stay with 1 or something.
So that's a great thought, except for remember, they both want to become stable, and only giving 1 wouldn't make that element stable. So let's just look at this one, because that actually answers that question. So I'm going to tell you that magnesium right now is Mg and iodine is I. So let's look up here. Let's find Mg and let's find I. And you tell me how many valence electrons magnesium has and how many iodine has.
Hey, where's Mg?
Mg is actually.
Oh, right here.
Do you see
It'll
it?
have 2. Yeah, it will have 2 electrons, right?
It has 2 valence electrons. And what about iodine? I.
Where's that at?
It's at bottom right. Number
We'll have 7, right?
It has 7. Perfect. So let's put our valence electrons on. We have 2 and we have 7. All right. So what happens first?
Can I look back at the other one that we just did? All right. So I think Mg would give 1 electron to iodine. What's it called?
Yep. All right. So now iodine, does that have its 8 valence electrons? Is that one stable?
No.
It doesn't?
Yeah, it does not have 8, right?
How many does it have?
7.
But it just gained that 1. We just drew that 1.
Oh, now we have 8.
So now we have 8. Is magnesium stable?
I would say no.
No, because it still has this 1 valence electron it hasn't done anything with. So let's think about, have you ever like made coffee or Kool-Aid before?
I made coffee, but I'm only made Kool-Aid like once.
Okay, so let's talk about coffee. Do you use 1 drop of water and 1 coffee ground to make your coffee?
Nope.
No, you
Nope.
use a lot of each one, right?
Mm-hmm.
All right, so it's the same thing with our compounds. I don't take 1 magnesium atom and 1 iodine atom and throw them into a container and just hope for them to react. I can't even find 1 atom of each because they're just too small. I'm going to take a bunch of magnesium and a bunch of iodine. I'm going to put them in this container and I'm going to make them react. So if I have a bunch of each of them, what's going to happen?
Just I don't know.
I have a bunch of iodine atoms and I have a bunch of magnesium atoms. And I know that I've used up all the electrons iodine can take for this iodine atom, but magnesium still needs to get rid of another one. So what's going to happen is I am going to bring in a second iodine.
Oh.
Because I have a bunch of them just readily available for me to use. So I'm going to bring a second one in.
So the other electron, the magnesium sort of thing?
Magnesium. You're good.
Magnesium. So now the other one that I had, you would add it to this one?
Exactly. Perfect.
All right.
And now we're going to write this into our ion form. So let's write this as ions. So magnesium as an ion. How would I write that? We have Mg. And what's my charge?
+2.
+2. Perfect. You're crushing it. All right. And then I have iodine. What do I have to put on my iodine?
But wouldn't you have to write another I since it was 2?
Yeah.
And you'll put -1 for both?
-1 for both. And we have to put our 8 valence.
And put the 8 dots on both.
And then we put our brackets.
Is it time?
It is time. I just want to talk about one more thing about ionic. So if instead of doing that, what we can do is these are going to be the exact same thing. So whichever way makes it easier. But if you just don't want to do it twice, you can always put magnesium like this with a +2. And you can say you have 2 sets of this iodine right here.
Oh, yeah.
Okay. So it works the exact same way, whatever way works easiest for you. I do want you to look at something for me, just so we remember that all of our ionic compounds the charge has to equal 0. Okay. So our charge has to add up to 0. So if we look at this one, magnesium has a +2, and then we have 2 -1s. So we have a +2 -1 -1, and that adds up to the number 0. So we have to
so the metal ones are on the left, right?
Yep.
So the metal ones will always like add up to 0.
So the metal plus the non-metal, when those two add up, when we make our final compound, they have to, the charges have to equal 0.
Yeah.
Okay. And then that's all the time we have for today. But does that make sense?
Yeah. Can I take like screenshots of that?
Yeah, and I will send you. I'll send you the video of it as well.
All right. Let me take a screenshot of this one. All right.
See everything on that one.
Yeah. Can I get the other one too? All right.
Right. And then I'll send you the video, and then try and watch the video on covalent drawing. And then you also have to remember that on the summative, there is naming and formula writing. So there's videos on those as well. And if you have questions over the weekend while you're looking at this stuff, make sure you're emailing me, okay?
Wait, so what can I work on? What should I work on after this?
So what I would recommend is, if we're looking at this, I would say try and do like another practice problem with that.
Or like on that whole week?
I would say probably for now skip that Thursday information and go into this one, Intro to Covalent, and do this assignment. This one goes through, there's a video on this one, so go through this assignment and learn about how to draw the covalent, because they're a little bit different, because covalent's 2 nonmetals where they both have like 5, 6, or 7 valence electrons. So neither one of them want to lose valence electrons. So instead, they are actually sharing their electrons. So that's what the difference is going to be.
Yeah, I'll try.
And
Attempt to.
then the next week, week 13, I would say go into intro to ionic naming, which is naming those compounds now. So going into the names and the formula writing. So do the sixth, the go through the sixth, then go to the 11th and do that assignment. Then go to the 13th and do the intro to covalent naming.
Mm-hmm.
And then once you have all of that done, I would say probably go to our yesterday's assignment and look at the review and see how well you can do on the review, and then try the summative. Because if nothing else, then you have at least some scores other than zero. And if you can't get to this summative before like Sunday, just send me an email and I will open it up for you like individually until like Tuesday or Wednesday, whenever you need it through. So that way you can take some more time to actually do the practice and actually understand the material, rather than just trying to get it done because it's due on Sunday. So if you do need more time, just let me know.
All right. Thank you.
Yeah, no problem. And then I'll send you the link to the video hopefully soon.
All right. Thank you.
Yeah, no
Appreciate it.
problem.
Have a good day.
Have a good day.